Everybody say hi to Seth.
Who's
Hey Seth. Hopefully you're watching this at home, or we'll watch it tomorrow. Okay, so, oh wow. Like and subscribe, ring that bell.
Well, it was 80 before, and now it's 24.
That's not bad. 24 is not bad at all. We should turn it off.
Yeah, I think that the speed wobbles should hell of a show.
All right, so forces. Forces are pushes or pulls. So we started talking about how things move, which is kinematics, acceleration, velocity, displacement. And now we're going to talk about why things move. And the why things move is called dynamics. And here's the thing about why things move. At the heart of movement is acceleration. Okay? So we know that the slope of the displacement time curve is velocity. Velocity causes displacement to move, or it causes displacement to change. And the slope of the velocity curve is acceleration. Acceleration causes velocity to change. Well, today, we're going to talk about what causes acceleration. And Newton's laws, there are 3 of them that we've assigned to him, are the heart of forces. So we're going to talk about some forces. So here's some fun stuff. I like this. This is an excellent example of Newton's third law. Do you see this?
Just die. Car and he pushes himself over.
It's like
You had to kick the tail light out? Is that what you do?
he was just trying to get the car, like, I hate you, rawr! Bam, bounces that off the concrete. Because that's what happens. That's instant karma right there. Does anyone know who this is? Actually,
scientist.
I am a rocket scientist.
I'm assuming it's a rocket scientist.
He was number 2.
Somebody, not Elon Musk.
No. So if Neil Armstrong was number 1, who's number 2?
Oh. Buzz
Aldrin. Yeah, it's Buzz Aldrin.
Neil deGrasse Tyson.
Oh, and did anyone know number 3? Michael Connolly? I think his name. There's a picture. It's the loneliest picture in the world ever, and it basically shows everybody on the planet except for him. He was in the pilot vehicle above the moon,
Yeah.
and he took a picture, and it has like the Earth behind it, and Buzz Aldrin, Neil Armstrong on the moon. It's like, here's everybody in the entire world except him. 1969. Everybody in the entire world except for the photographer. But anyway, so forces are pushes and pulls, and their units are newtons, named after the cookie. Not named after the cookie. Who was the Newton named after?
Isaac Newton.
Isaac Newton. You know what Isaac Newton did? He invented calculus. So when you're like, I hate this calculus, you can blame Isaac Newton. Do you know why he invented calculus?
Circles.
No reason.
Because it helps understand dynamics, maybe?
Exactly right, yeah. Isaac Newton invented calculus because the math didn't exist to correctly model moving objects. So he had to come up with a math system that correctly modeled moving objects, and that's calculus.
Scatter plots and stuff?
Slopes and slopes of curves and areas under curves.
Okay.
So yeah, he's like, the math that we currently have, basically arithmetic and basic algebra, didn't correctly model the motion of objects as they moved, and specifically the motion of stars and planets. So he came up with it, which is pretty cool. All right, so quick review, kinematics. When can you use velocity equals acceleration times time? When you have an acceleration that is average or constant. So a little bar means average. So you can use change in velocity equals acceleration times time when your acceleration is constant or you have an average acceleration. Here's the good news. When we're doing math, acceleration will be constant. And when can you use displacement equals velocity times time?
Constant velocity is
Constant velocity or you have an average velocity. So you can use this equation when you have the average velocity or a constant velocity. V bar means average. Okay? You cannot use this when your velocity is changing and you don't know what the average is. And then displacement with constant acceleration, and you can use this anytime. Okay? Assuming that acceleration is constant. And VI is initial velocity. Does VI change? No, VI doesn't change. Now remember, if you're talking about velocity or displacement in the vertical direction, dy, vy, a doesn't matter, ay. remember, horizontal and vertical displacement, or horizontal and vertical movement are independent of each other. And then, if you happen to have no time, but you have acceleration, velocity, and displacement, you can use our favorite vs squared equals vi squared plus 2ab, which is basically this and this put together. Okay,
What
quick
was
review.
VF again? Velocity finite?
Fine. Yeah, velocity finite. Okay, so quick review of kinematics. Anyone have any questions? Our unit test last Friday was Friday, so that means this Friday is the deadline for any retakes or makeups or old work. Capiche? Comprende? Verstehen? Understand? Yeah, cool. Is gravity a force?
Yeah.
There's little quotes there, so I'm gonna say
Yeah. So if I take a ball, where's my little orange ball? Come on. If I take a ball, is this applying a force on my hand?
yes.
Yeah. But if I do that, and I move my hand away as fast as the ball is falling, is the ball applying a force on my hand while it's in the air? No.
But isn't gravity applying a force on the ball?
Sort of. That's what we'll get to. So let's discuss this. So right now the ball is applying a force of gravity on or a force on my hand, right? But if I take my hand away, it's no longer applying a force when it's in the air. So is gravity technically a force? No, because there's still gravity on this, but it's not a force. We remember that gravity is an acceleration. So gravity is an acceleration, weight is the force. So when we're talking about force, we use weight. And weight is given the symbol, oh geez, it's been like 10 years, I still haven't changed this. We don't use W. Unbelievable, come on, Byron. You got a FG, we use F sub G. Okay. I changed it on the poster. We don't use W. W is something else. We use F sub G, which is just force sub gravity, the force of gravity. Yes, W is word, exactly.
Wait, so F of G is mass times gravity?
Yep. Fg equals mg. Mass of your thing multiplied by gravity. So mass of your thing multiplied by gravity, acceleration due to gravity. So you will have the same mass on planet Earth as you will on planet Mars. But you won't have the same weight because the acceleration due to gravity on Mars is about 5/6 that of Earth. It's like 6.5. It's like 6.6, if I remember correctly. Or 8 or something like that neighborhood. Anyway, it's less. So you have less gravity on Mars, therefore you have less weight on Mars. But your mass is the same. And we will find later gravity depends upon the distance of percent of gravity. I don't think we do that anymore. This one. So, okay, so what has a greater weight, a tennis ball or a basketball? Question, room.
Oh yeah, so I remember I was thinking of a thing, it was kind of about like everything has its own gravity, whether it's small or big, just, yeah. I was thinking about that, right?
Yes, that is Newton's law of universal gravity,
Okay.
which is expressed in that formula right there. Fg equals gm1 m2 over e squared. And we will discuss that when we get to circular motion.
Okay.
Yeah, because it's why the moon circles the Earth, it's why the Earth circles the sun, and so on and so forth.
Yeah. Okay, cool.
So, which has a greater weight, a tennis ball or a basketball?
Basketball.
Not a trick question, a basketball. Which has a greater acceleration when you drop them?
They both have the same acceleration.
Yeah, both have the same acceleration. So this was demonstrated by Galileo. So before Galileo, we had philosophers. Philosophers were the earliest scientists of their day. The problem is they were rich and they were fuddy-duddies. And if you were a philosopher in ancient Greece, you didn't really do anything. You talked, you thought stuff through, but you didn't really do anything. Not till like Archimedes and Aristotle came along did you actually, hey, we can build stuff. So Aristotle thought, since a bigger rock hurts more when it falls on you than a smaller rock, then there must be a greater downward tendency for a larger rock than a smaller rock. He called this natural motion. He says objects have natural motion when they move, and a bigger rock has more natural motion than a little rock. So it must have a greater tendency to fall. Galileo did the experiment, he took 2 physics students and he went to the top of the Leaning Tower of Pisa. And he took 2 physics students, and under one of them, or over one of them, he had a small rock, and over the other one he had a big rock, and he dropped them both. And did he hear ow, ow, or did he hear ow?
Heard ow.
He heard ow. He didn't hear ow, ow. So that's the story.
Really?
So you- no.
I feel like it'd be more dead.
It's apocryphal. It's a parable. It's apocryphal. So that's just like Isaac Newton and the apple, also apocryphal, which we're going to talk about. Actually, since might as well talk about it. So you guys know that I can't remember how much PBS you guys watch, but you know Isaac Newton is associated with a falling apple,
Yeah.
and they have like an apple falling on his head.
Yeah.
Well, the story goes that Isaac Newton was under a tree one day, and he noticed that apples were falling from the tree. And he thought, I bet those apples fall towards the ground at just as fast as planets fall towards the sun. And he used this idea to basically say, I'm going to postulate that all objects fall at the same rate, just like all planets fall at the same rate. And he knew that all planets fall towards the sun at the same rate because this guy named Johannes Kepler, quite a few years before him, he had done some math with the location of Venus and Mars and the Earth. And he's like, this goes this fast, and this goes, hey, look at that. And he did some math to find out that all the gravity that the sun exerts on the planets is a function of radius, which is kind of fun. So he used all this information and he came up with this.
I feel like the fact that it went straight from apples to planets is a little like.
It went from planets to apples.
Yeah, it went from planets to apples.
Planets to
yeah,
apples.
he's like,
Because
the gravity force that the planets, or the sun exerts on the planets, varies with radius, square radius, actually. And he's like, I wonder if that's the same case for apples falling towards the Earth. That's the parable. That's the story. And they do. And again, we'll talk more about what creates gravity in a future unit. All right. So dynamics. Yeah. So dynamics is the study of why things move. Forces are pushers of poles, and they are vector quantities. So here's a new symbol for you to add to your repertoire, and it's a half arrow written over a variable. That half arrow written over a variable tells you it is a vector. Meaning, a vector has what?
magnitude and direction.
Magnitude and direction. So it's a vector, so it has magnitude and direction. So it matters. Direction very, 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 very much matters. Okay. So some common forces. Weight is F sub g. Weight is F sub g. If you are currently exerting a weight, raise your hand. If you have weight, raise your hand. So it looks like almost everybody has a weight, except for Adam. Adam is weightless. So everybody has a weight except for Adam. What's keeping you from falling through your chair?
If you don't weigh too much to break the chair.
The chair is exerting something upon you?
A reverse?
A reverse force, yeah. So we're going to call this reverse force normal force. So a normal force is a resisting or a balancing force that it always exists perpendicular to a plane. So the plane in this case is the parallel plane between your butt and the chair. It's butt plane. So you're applying a downward butt force on your chair, and your chair is applying an upward normal force against your butt force. Now, when two vectors that are opposing each other are equal or balanced, we say you are in equilibrium. It's a little bit different equilibrium than chemistry equilibrium, but we say we are in equilibrium when our forces are balanced out. So you are applying your downward weight on your chair, and your chair is applying an upward normal force on your butt. You are in equilibrium. and the sum of the weight of you and the chair is exerting a force on the floor, and the floor is exerting an upward normal force on you. You are in equilibrium. How do you know you are in equilibrium?
From not breaking the chair.
You're not falling through the chair, exactly. You are not falling through the chair, nor are you doing what?
Getting moved up.
Getting launched up.
Nor are you getting thrown forward or upward, getting launched upward off your chair. So here's the crazy thing about normal force. Normal force is a variable force. It can get larger or smaller because it's a balancing force. There is an upper limit, but it changes based on what is exerted to it. For instance, Eli is exerting a force, I'm going to guess 700 newtons on his chair.
Dang, Eli.
His chair is exerting 700 newtons back on Eli. Now, if Adam sat on Eli's lap, then the two of them would be exerting a force of 1,300 newtons down. Would the chair exert 1,300 newtons up?
Both of them.
Yeah. I've seen some pretty big girls sit on the chair. Yeah.
So like the point to where an object would
Dang.
Hey, Scott's asking a question.
the point to where an object would break, so say you just keep stacking rocks and like a big stick and then that stick snaps, that point to where it snaps, would that be when it can't exert any more force upward?
Correct. Yeah. That would be at the point where we have exerted we have exceeded its ability to exert normal force.
So that would be like the
Yeah.
upper limit?
What about something that like Ed would say?
Yeah.
So it can't hold its shape, but it bends.
We'll talk about elastics later on, but still, that even though it's bending and not breaking, it's still exerting an upward normal force. So then, if Chris added to the Eli Adam pile, then we might be exerting 2,000 newtons of force, and that's where you get to a point where the chair would no longer be able to exert a normal force. Make sense? Okay. So I have something else for you. It's very related to this guy right here who tries to jump off I don't know what that thing
Yeah,
is.
I'm not that.
So he jumps, and analyze this GIF because this is important. Why is it that it'll hold his weight until he jumps?
Because you
Five
need
more
force.
force.
You need more force to go up and get off.
And I'm going to need a volunteer.
I'm not trying
Dude, I'll
Who
freaking
can
break
do a
myself.
backflip?
Come here.
Alright,
to.
I'll do a flip.
Have fun in this world.
R.I.P. And then I decided to
Hard kid game.
R.I.P. Rome.
Oh, yeah, dude.
So,
And this is how then.
I think I'm going to put this on the main screen. Cal right now,
I'll do a flip.
You want Rome to die?
Whoa,
Yeah.
Jesus.
Euro.
Get in here, you hoe.
All right. I'm going to try to move this over here. Oh, where'd it go?
We got a meal once, dude.
Right over here. There we are. Okay. So there we are. So go ahead and stand on the force plate.
Alright, let's see how many force like Oh, I'm not
640 newtons. Now, guys, this is excellent. What is Rome's mass?
A lot.
based off his force.
Yes.
Oh.
Exactly. 63 or 64? Exactly. So again, weight, mg, is equal to mass times gravity. We know gravity to be 10, so his mass is 63, or let's go for 64 kilograms. Make sense?
How much is that in pounds?
Multiplied by
2.2.
yeah, multiplied by 2.2.
Sick. I can't do math with that.
140.
Sick. Alright.
So, okay, so does that make sense? It's very simple. Take the mass, multiply by 10, you got weight. Take the weight, divide by 10, you got mass. Okay, now this is what I want you to do. I want you to do a bunny hop, just a second. So, a bunny hop. No, not quite yet, but soon.
41 pounds.
I'm not sure you're in the right shoes for this, but we'll give it a try.
Can you
So,
barefoot?
this is how I want you to jump. I want you to bend your legs like this and jump like that.
Okay.
Not yet?
Oh.
Okay. So I'm going to start collecting, and it's actually going to start right here. So it might, I'll shrink this down a little bit. I'm going to start collecting data.
You want me to do
I would like you to sketch what you think the graph is going to look like when Rome does his bunny hop.
You want me to do this multiple times?
Just one second. Not quite yet. So you're gonna bend your knees and you're doing a little bunny hop. You're just gonna go hop and land back on the force plate with your legs bent, knees bent. Okay. So sketch. What do you think the graph is going to look like of force over time? It's going to go boop, 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 boop. And when it gets right here, Rome's going to jump. What's it going to do? Make a little sketch.
Just set your hair on fire. What? Yeah, I did Saturday night.
All right. How we doing? We ready?
I'm ready.
Okay. Hitting collect. We are collecting. Do your bunny hop. Excellent.
Wow, I got that
Thank you very much.
I got that right.
Okay. So let's take this graph apart because this is an excellent graph.
My EKG be like.
First of all, this is 0. Okay.
Yeah.
What's going on right here when it's 0?
He's off the.
Yeah, he's in the air. He is in the air. But something really interesting happens right here. So we got your 640, and then whoop, what happened here?
Well, he started to get the lift.
Starting to go
before
up,
she
the
was
weight's
doing
coming off.
It's when he went down.
Yeah.
So when he went down,
Okay, I
have
get
you
it.
ever experienced this in an elevator where the elevator starts going down? You go like, "Ooh!" You get that little like weightless feel in your
Yeah.
gut, where your stomach is like moved a little out of the loop. And so that's what's happening. He has slightly understand, guys, that the force plate isn't measuring weight; it's measuring the normal force it's exerting, which is hopefully equal to his weight. So, boop, 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 and he drops down, and it goes bloop, and then, boom! What happens right here?
He jumped.
Yeah, he jumps in so much as he is squishing the molecules of the force plate. He's like, squish! Squish the molecules of the force plate. He cannot jump off the floor without the floor. You ever tried to jump in sand?
Oh yeah, that sucks.
Not easy. You ever tried to jump in water?
Yeah.
Not
It's
easy.
called swimming.
Remember, like, when, if you try to jump in water, the water moves out of the way because the water can't exert very much normal force.
Unless you Jesus.
Unless, yes. Anyway, so he squishes down. Now he squishes the molecules, and what do the molecules do? They push back, right? Squish molecules, they push back. Here he leaves the plate, boom, and now what happens when he hits the ground?
It pushes back.
Molecule squish. He squishes the molecules again.